Okay, let's see. Okay, are we ready to chat about this? Okay, I apologize for what is honestly the silliest setup possibly ever. Okay, all right. Yes, I'm a computer science instructor. Yes, my USB-C port is officially dead, and I'm now document sharing a Surface, which is absolute bonkers. Okay, this is the graph from the warm-up. I think it would be easier if we sort of walk through it together. So we've learned two different MST algorithms. We've learned one called Prim's that goes vertex by vertex. And we've learned one, which we're going to be focusing on, Kruskal's, which goes edge by edge. So does anyone remember the very first step of Kruskal's? There's sort of like a preliminary step that we need to do to sort of figure out how we're going to assess whether or not an edge is included in the set. Which edge are we going to look at our very first time? What's the first edge we're going to consider as a possibility to add to the MST? Anyone remember? Yeah. The smallest edge. And so, in fact, the very first step of Kruskal's is to take all of the edges and order them. And we're going to start with the smallest. So, which edge in our current graph is the smallest? What do we see? 5. I agree. So you could like go out and like sort of write up like, oh, like maybe A, please let me do this. A to D, that's the smallest edge, that's 5. Or I'm just going to kind of draw it here. And what we're going to do in Kruskal's is we're going to start off by sorting the edges. And then we're going to do this funky thing where we're going to initialize each vertex to its own component. And so what that means is right now, I'm kind of like imagining an overlay of this graph where it's just the vertices and no edges connecting them. So I just sort of see vertices. We kind of like, sometimes people call this the island method. Like each vertex is a little island unto its own. And then as we add edges, we think of those as sort of being the bridges between those islands that then connect them together. And we just go edge by edge until every single vertex is then connected to every other vertex. So right now, everything is in its own individual component. So A and D are not already connected. And so I'm going to ask myself, well, with the smallest edge, 5, do I want to include that? Will that increase the connectivity? And the answer is pretty much always going to be yes, because unless it's a self loop, the very first edge connects at least 2 vertices, and if everything originally is not connected. And so I'm going to sort of like draw a line here and be like, yes, we've officially selected that. And so now A and D are connected to each other, and everybody else is still off in their own little island. Which is the next edge that I want to look at? I heard it. The other 5. Yeah, so we notice there's actually 2 edges with the weight of 5 here. So here's another one. Boom, right there. This edge is currently starting and terminating somewhere in between C and E. And so the question I'm going to ask myself is, in this current state, are C and E in separate components? And thus, would adding this edge join those 2 components together? That's the same question, just in a weirder way to say it, because I'm setting us up for the rest of the lecture. Is this going to increase connectivity? Do I want to include the edge C to E? Yes. So I'm going to also mark this one. And now C and E are connected to each other. And I'm just going to keep track of this. Great. Okay, what's the next edge that I need to look at? The 6, D and F. Perfect. Okay, so here's that 6. And so right now, we see that that 6 touches this component, which is the DA component, and this component, which is just the F component. Do I want to add 6? Will that increase the connectivity? Yes, I agree. So I'm going to add this one as well. Now, I've got, at this current state, I've got one component with 3 vertices in it, one component with 2 vertices in it, and then a B component and a G component. They're kind of still hanging out by themselves. I'm going to just make sure that I don't forget that. Okay, where do I look next? A and B. And also, because apparently past KC chose chaos, there is another edge, B to E, that is also the equivalent weight. Now, here's the weird thing. Ignoring the fact that there is a 7 between the B and the E, if I was just looking at the A to B first, would I include that edge? Yeah, I see nodding. Yeah, that B is not connected to any component. So if I chose this edge, now B is connected to that component. That's great. I'm going to loop back around, and now I'm going to examine this edge here with the 7. Do I want to include this edge? Is this edge going to combine together two previously disconnected components? Yeah, right? So here we go. Now, what that did was it took our two sort of bigger components. Now we have only two components left in this entire graph. One big component that is C, E, B, A, D, and F, and then another component that is G. What is the next edge that I'm going to look at? The 8s, right? So we've got 1 8 here, B and C. Do I want to include this edge? Good job. Yes, you are correct. We do not want to include that edge because B and C are already part of the same component. If I were to add that edge, I would end up with a cycle, and cycles mean we have more edges than we need. We're trying to find the minimum spanning tree. Yes. Sure.
So if you want to get B to C, right?
Mm-hmm.
Her weight is 7 plus 5, which is 12, but A is smaller than 12.
So I think what you're asking me about is like the weight, like the total distances between things.
Yeah.
Yes. Sorry. And in this particular case, we don't care about the distance between two specific nodes. What we're really trying to do is, if it helps, like to think of that like electrical company analogy, or sometimes I think of it as like road builders. Like I want to spend the least amount of paving money. And so that's going to be this set of edges, even if that means in order to actually get from B to C road-wise, I have to do like, this is a much longer way for me to travel. That's okay. Yes. Good clarification. This is absolutely going to confuse you between cross skulls and Dijkstras. I understand. Okay, we have one more 8 edge on this graph between E and F. Do I want to include E and F? No, because these two things are already connected. Now, to that previous question, if I actually wanted to travel between E and F, like if I was trying to find a shortest distance, that would be really inconvenient because I'd have to go E to B to A to D to F, right? Again, MSTs are not solving that problem because they would be very bad at solving that problem. Now that we've looked at those, we've got a couple of 9s. Let's start with this one. Do I want to include this 9 right here between B and D? No, those things are already connected. Now I look here. Do I want to include this 9 between E and G? Yes. Finally, G has joined the rest of its brethren. And there you go. The green lines now represent the MST. Any questions on how this algorithm sort of like functionally works? Yeah.
Would you stop looking there, or would you filter through the rest of the branches?
Ooh, good question. Do we stop there or do we filter through the rest of the branches? So right now, our human brains immediately looked at this and knew like, hey, this now represents full connectivity. So yes, I would stop because there's no more vertices left to include. So as long as I can answer that question, like have I achieved full connectivity across all vertices, then I can stop early. Yes. Yeah.
So hypothetically, like there isn't just one unique MST if there are like equal weights between vertices, right?
Yes. For the recording, there is only a unique MST if there are unique edge weights. If there are duplicate edge weights, there could be multiple possible answers to this. Right? Like, I can't even remember, but you can see sort of the order that we did it in a couple situations. Like, The reason that I chose to look at this 7 before this 7 was just like, that's the order in which they're maybe stored in my collection. It's kind of arbitrary. And so you can imagine somebody would implement it in a way that maybe I would look at this 7 before this 7, and that'd be okay. But MSTs are unique if the edge weights are unique. Otherwise, there could be multiple MSTs. Any other questions? Okay. Great. All right. So now that hopefully we feel comfortable with the Kruskal's algorithm, we're going to talk about how you implement this, which is exactly what we're asking you to do on Project 4, which comes out today. Haha. Very exciting. Your last project. We are in the final lap of the class, y'all. Week 7, you've almost made it. It is spring quarter. I know things get real hard to focus from here on out. It is also a sunny day outside, so props to you for choosing to be in this basement right now. But reminder that Project 3 is due today. That's your heaps assignment. Project 4 does come out. Just as an FYI, Project 4 was originally designed to be a individual 2-week assignment. But I have now taught this like 6 quarters in a row or something, and I'm like, I don't know who was thinking that, because that's crazy. This is a way bigger project than any of the other projects you've done so far. And there is a reason that we do that. This project in particular is pretty application heavy. There is a graphical user interface, a GUI. You're going to get to see some visualizations. The idea behind this project is that it's the kind of thing that if you need to put something on your resume as a sort of elongated project and you can talk to people about, that's our goal with this one. That is also me trying to justify what will probably be an uncomfortable experience at some point in your journey through Project 4. So Project 4 does come out. It's due in 3 weeks, which would be the Wednesday of our last week of the quarter, which is June 1st. We have added this quarter for the first time a checkpoint. So on 5/22, that's like the middle point between now and when the project is due. If you have achieved at least 15 points on Gradescope, you are going to get extra credit, if that is what your Gradescope is looking like, by 5/22. That extra credit will probably be equivalent to, I'm going to go into your set of poll everywhere participations, and I'm going to add 3. So you can think of this as like 3 extra credit points, where each, lecture poll is 1 extra credit point. This is not us trying to punish you. This is straight up us just trying to give you some incentive other than Casey saying, please start early, otherwise it will be uncomfortable. We're trying to carrot you into getting started early. So please, please, please do start on this. It will get confusing. You will struggle to get started. We all do. So it's also a great time to show up to office hours and get some help working through the beginning pieces of this. Exercise 4, the graphs exercise, is due this Friday. We did take a quick peek at Gradescope. Does it look like people have made a ton of progress yet on exercise 4, which I'm going to assume means we're all just brain dead from midterms, and also P3 is due today. But reminder that is due on Friday. We are going to have another exercise come out on Friday. It will also be about graphs. And then, sorry, it's not that 2 more exercises are coming. It's 2 if you include exercise 5. Our last exercise will be exercise 6, which will go out not this Friday, but a week from Friday, and then be due, because that'll go out week 8. That'll be due then week 9. So then week 10 of the quarter, the only thing that's going to be due is on that Wednesday will be Project 4. And then we're going to open up the final exam take-home assignment on that Wednesday of week 10. And it'll be due Wednesday of finals week. Yes?
Is the final exam going to be similar to like the midterm or like something different?
Is the final exam going to be similar to the midterm? Y'all, we in the thick of it. We trying to grade these things. I know I said it was going to be an experiment, but it is kind of a pain in the arse to grade. So we are going to probably make some pretty dramatic changes. I will promise you that it will still be take home. It will still be open note. And it will not be any type of time crunch like that. but we are sort of exploring different ways to make this process easier for all of us. In fact, I will probably release a feedback form. So if you have any thoughts about how this sort of experiment went, love to hear how things went for you. If you have any suggestions, things like that. And we're going to try a new version for the final. So thanks for being the quarter where I decide to transform exams. I promise I'll tell you as soon as we have finalized those decisions, so you have a heads up. Yeah.
With regards to Project 4,
Yes.
Do we have enough material covered to get started on it?
Oh, great question. After today, the answer is yes. So today's lecture is titled Disjoint Sets. Friday, we're going to finish up our conversation about disjoint sets. There are 3 parts to Project 4: disjoint sets, implementing Kruskalls, and implementing Dijkstras. You've already learned the algorithm for Kruskalls. You've already learned the algorithm for Dijkstras. We just have to finish up the disjoint sets portion. So you can definitely get started now, but after Friday, you'll have absolutely everything you need. Good question. Any other administrative questions? Okay. Let's dig into it. Okay, these are mostly review. Remember, we learned about this sort of MST thing. Why does this work? Because of the idea of this greedy algorithm where we're sort of making the best choice possible at each individual step. We adapted Dijkstra's to be Prim's algorithm because that's sort of like a explore out from vertex by vertex situation. Kruskalls is that different approach. That is the sort the edges that we just did. Here is a visualization of Kruskalls. So we add that, we add that, we add that, and we kind of see how these components build up, things like that. Okay, remember I tried to show you those YouTube videos? I could not find those YouTube videos. Apparently somebody has taken them off the internet, but I found stills from them somewhere. So these are stills from those super helpful videos that are now lost to the internet. And so what these are is you can see in the sort of light gray, that is the graph as it originally is designed. And then the dark black lines are that overlay of us exploring over the graph. And so in Dijkstra's, you can see there's that sort of source point in the middle there, and then everything kind of builds out from that. Prim's algorithm, you can see it kind of has the same source, but see how it kind of turns into one long spindly path? That's kind of what's happening. Kruskalls is kind of building up a path as it goes. I did find not this still, but a slightly less good, but still helpful video that visualizes Kruskalls. This is more of a visualization of what Kruskalls does, where we're not going vertex by vertex, but rather we're sort of jumping around to different edges, and eventually they'll all end up combined. So where Prim sort of starts at one vertex and worms its way around pathwise, Kruskalls is kind of grabbing edges until all of the islands are beautifully connected into one archipelago? I don't know. I should take biology or geography. See, that's how bad I need it. So just to give you some sort of sense as to the differentiations there. So that's the algorithms. How the heck do we implement these things? We're going to meet a new data structure today, the disjoint set. Sorry, we're meeting a new ADT today, and I'm going to tell you about the data structure that implements it. So this is our Kruskalls pseudocode. And remember at the very end of lecture, I mentioned this, there's this sort of line here that I think previously said things like initialize all vertices into their own component. Or you could say it this way where you're initialize each little individual MST as a single element MST. But this is that idea that we're going to look at all the vertices of the graph and we're going to kind of mark them as their own independent islands. I'm going to call those things components. And then as we go through, we're going to check for every edge, hey, which component does that edge connect to on one side? Which component does it connect to on the other side? And are those two components different? Meaning, will this edge bring together two previously disconnected components? And if that is the case, we are going to union those two things together and add the edge to the MST. So we need this sort of structure that's going to keep track of these components and enable us to mark them as now connected as we add in the connecting edges. Welcome to the disjoint set ADT. So, disjoint set is an ADT that is a family of sets. It is a set of sets. And then what you have is that each set has a representative or sort of like a unique marker. And of these sets, you can make a new set with a given value, and you can imagine this makeSet. That's what we're going to run on this line here, where we're going to initialize every sort of vertex as its own independent set. We're going to run makeSet on every individual vertex. We can pass in an individual vertex and figure out which set are you a part of. So that's kind of what's going on here with these finds. And then finally, the third function that we have to implement is this idea of union, which is happening down here, which is, okay, now I want to mark these sets as officially combined, i.e. I've added an edge that connects them. The disjoint part of it is that this requires, like all sets require, unique values. Remember, sets can only have unique values. So disjoint sets, all the values must be unique across all the sets, because if you typed in find and you had duplicates and maybe those duplicates were like in different sets, the whole thing would break apart. So disjoint really refers to that sort of idea that there's no shared elements, no duplicate elements, but otherwise you can think of this as a set of sets. Here are some slides about what Project 4 is going to be. Project 4 is all about mazes, particular computer science obsession. And actually, as it turns out, there are some pretty, I'll say, non-complicated, because it's not simple, but there's some pretty non-complicated adaptations to the things we've done to both generate a maze from scratch and to solve a maze from scratch. So for example, if you were to solve a maze, it's kind of like you're trying to find the shortest path through any of the pathways. And so that's what you're going to use Dijkstra's for. You're going to run Dijkstra's over a graph that represents a maze, and then the resulting shortest path will be the solution of how you walk through the maze. How you generate a maze is when you need all of the sort of like places you have to go in the maze to eventually be connected somehow, but you don't necessarily need them to be connected in efficient order. You just need, for you to be connected through all the pathways. You can walk through all the doors, however you want to visualize this maze. The generation then is creating an MST. So we can generate mazes by creating an MST. We can solve a maze by running Dijkstra's over a graph. This will make a lot more sense. There's a ton more details. As you know, our assignment write-ups are quite thick, so please feel free to read all of it. There is a graphical user interface, like I mentioned, that will show you the mazes that you generate and show visualizations and animations of you actually like walking through and solving the mazes. So it should hopefully be a pretty good time. Yeah. But that's where our North Star is. Let's talk about this thing called disjoint sets. So the disjoint thing, like I said, is that refers to the idea that there are no common elements. So for example, here on the left-hand side, we have set 1 that has Eileen, Kevin, and Keanu in it, and we have set 2 that has Leona and Shardil in it. There are no duplicate elements. These two sets combined together are what we might refer to as a disjoint set. If we look at the right-hand side, we can see that Santino is represented in both sets 3 and 4. That's a duplicate, not disjoint sets. So in computer science, this disjoint set is the collection of these sets. So what we've got is we've got a set here of unique values. It has some type of an identifier. We're kind of calling this set 1, and that is separate from this grouping, which is called set 2. And this sort of gray box around all of them, that's the disjoint set. Yep. Wait. Hang on. Let me just make sure that I'm using the right version of these slides. Okay. All right. Just kidding. I thought I hid these slides, but maybe I didn't. Okay, cool. Just sanity checking because I was moving stuff around. Okay, so let's talk through, in theory, how each of these functions work, because you're going to be implementing these functions. You're going to make a disjoint set. You're going to be implementing these functions, and you're going to use these functions to implement Kruskal's algorithm. Just like I showed you sort of highlighted in that pseudocode on that first page, let's talk about how you actually do it. So here, if we want to find set, the way that this works is if I call find set of Brian, it's going to need to do something where it looks through every single thing until it finds, hey, look, here's Brian, and then it's going to return back for me 3 being the representative of this set. Find set of Sherdil will return 2. Find set of Velocity also will return 2. That's the representative of anybody that happens to be in this set. So when we're doing that, hey, are these 2 vertices in different components? We're going to check if the 2 results of find sets are equivalent. So if I call find set of Kevin, what am I going to get returned in this case? 1. I agree. If I call find set of Eileen, what am I going to get returned? 1. So is this test right here true or false? True. Agreed. Yes. Questions or suggestions? Yes.
Like the representations,
Mm-hmm.
are they returned as primitive data types or object data types?
In this particular case, they are probably primitives, but the way we're going to implement it is you actually are going to probably return not an integer number, but one of the like values themselves. Yeah, dot equals. Thank you. Yes.
So that means that for the entire disjoint set, there are no duplicates within any of the subsets, right?
Correct. Across all 4 of these sets, there can be no duplicates. Yes. Okay, so that's how find sets is supposed to function. Union, which will be the function that gives you the most headache, heartache, triumph, I don't know. It'll be the one that takes the most time. Union, so if I call union on Blairy and Brian, I would say initially go, and technically inside union is a call on find set. And so I would call find set, and I'd find out that Blairy is in set 1. And then I'd call find set on Brian. I'd find out that Brian is in set 3. And then I'd realize what I need to do is I need to union together sets 1 and 3. And what that results in is instead of having 4 original sets, now I've combined 2, so I only have 3 remaining. And you can see what then happened is I sort of took both Brian and Keanu and like pulled them into set 1. So set 1 is now the combination of all 5 of these delightful TAs from spring, I believe, 21, or spring 19, I can't remember, into one sort of bigger set. Yeah.
And then can we do a self-join and like what that looks like?
Ooh, if I did a self-join, it would just tell you what would happen essentially is like if I tried to join, let's say in this state right here, let's say I tried to call union on Brian and Vivian, it would return, both of them would return 1, and it'd be like, they're already done, self-unioned kind of thing. So it just wouldn't do anything. Yeah, yeah. So there will be a test, like I said, within union, there's going to be a call to find set on both items. And if the items are already in the same set, my work here is done. Yeah, yeah.
So then the set of value D would just disappear then, right? So like it would just go away, and you would only keep the set of value A.
Yes. And I am going to talk ad nauseum probably for most of the lecture on Friday about how you figure out which set absorbs which set. So there can only be one, and we will have very specific decisions about which one absorbs the other. But for right now, just know that one does. And then finally, the only other thing we need to do is we need to initialize sets. Sets usually initialize, as a single item. So if I wanted to call makeSet of Elena, then Elena gets to be her own little set here, and it's added to our collection. If I make a set of Anish, then that's set 6. Man, maybe this is spring 19. Okay, anyway. I was like, when was the last time I saw these lovely humans in person? Cool. Be a TA that makes my slides, and then your names will live on for forever, apparently. Okay, so this is another just sort of description of the disjoint sets. So here's the set, right? Like this is how I would maybe visualize a regular set. This is how I visualize a disjoint set. No required order. Things have to be unique. Each set has a representative. We have those three functions. So let's talk about how this might work if we were to sort of start from beginning and build this up. So I'm going to call a new disjoint set, and I'm initially going to call makeSet of A. Oh, great. My animations, you really going to be like this? There we go. Okay, imagine this cloud appeared after I called new, and then I call makeSet of A, and I show up with a set of a single item, and I'm going to give it a representative of 0 in this case. Then I'm going to call makeSet of B, makeSet of C, makeSet of D, makeSet of E, and now I've got 5 little islands floating about in my disjoint set. Then I'm going to call find set of A, and find set of A, the animations, that would return 0. Find set of D, that would return 3. And then finally, I'm going to call union on A and C. When I call find set of A, I realize its representative is 0. When I call find set of C, I realize its representative is 2. So in this particular situation, what's going to happen then is those 2 items are going to get merged together. Yes?
Is there a way to just move one item from one set to the other without having to like do the entire union?
Is there a way to move a singular item to sort of like cherry pick an item out of a set and move it over? No. Once you are part of the community, you all act as a unit. We are really devoted to family ties in set land. So if you're marrying one of us, you're marrying all of us. Yeah? And so in this case, if I, for example, am unioning B and D, I would call find set. I'd realize that they have 2 different representatives, and then I would finally have a sort of merging of those 2 items. So if I call find set of A and find set of C now, I will return true, and find set of A and find set of D, that will return false, because A is over here and D is over here. Okay, let's talk about the actual implementation. So what you are actually going to be coding up is something we're going to call a tree disjoint set. And you're going to need to make a couple little objects to support it. So the way that the tree disjoint set works is we're going to start with a collection of many sets. We're going to literally call that a forest, because it's a collection of trees, and computer scientists love that analogy. And then here's this kind of weird thing. We're going to have this item called node inventory. And node inventory is going to be a separate field, a separate collection. You can see this is like a map. And it is going to map from node values to wherever those node locations are. So you can think of this as just a big collection of pointers. And the reason for this is because we've got these sort of islands floating about. And remember in Java, if you say drop the connection to something, that eventually the garbage collector will just come by and like swoop it up. In this situation, we're going to be moving these pointers around so much. I don't want to have to loop over everything and re-find it. So I'm going to have a separate data structure, a map, that is just going to map from value to the actual memory address of wherever that node is. So that's kind of the weird part of this, and I will show you some visuals for this. Other things to recognize is that we do need this idea of like a sort of set node. And the set node has to, know its data, and then it needs to have a collection of children. And for context, these trees are not necessarily binary trees. These are n-ary trees where you can see we have a collection of children, and that children could be sort of any particular number. The tree set, functionally wise, you need to be able to add something to an individual set. You can remove things from the set. And then we also need to be able to call this get representative. And that get representative returns the data of the overall root. So to your question earlier, I was showing you those sort of representatives of like 0, 1, whatever. That's the like ADT stuff. Now that we're talking specifically about the tree disjoint set data structure, In that situation, I'm going to use this tree set data structure, and that one is going to make the design choice to mark the set representatives as just the data of the overall root within that tree set. Let's look at some visuals. So now we're going to implement makeSet with this idea of this tree set data structure. I'm going to make a set. What that means is I've originally got my forest up here. My forest has no trees in the forest, but I'm going to start by making a set of 0. Ugh, animations, why? And so I'm going to make a set of the value 0. And then, sorry, it's a really subtle color. This little collection down here, that is my node inventory. And so at the moment that I make a set with 0 in it, what I'm going to do is I'm going to make a new tree set. That's sort of like this purple, like rounded square in here. And then I'm going to make a like set node that actually stores the 0. And the tree set's overall root is going to be 0 because it's only got one node in there. So that's what I need to happen there. But then in my node inventory, I've got this sort of array sort of representation here. You could have a map. And I'm just going to mark, hey, something that is marked as 0, here is the pointer to where to find that specific node. So this is a pointer to a set node. So if I call makeSet on all the other ones, I'm just storing those pointers here. So I don't have to loop over everything to find something. I'm going to use that like probably hash map lookup to find exactly where is the pointer to the specific node I'm looking for. So that's how we initialize the tree sets. Right now, we've got like a forest of saplings, if you will. Like all of these have just like a single root, right, inside each of them. Yes?
Could you add an element into a single set?
So you have to use union. So for example, if I was like, hey, I have a value 6 and I want to just like stuff it into the set that already has the 0, I can't do that. What I would have to do is I would have to call makeSet on the value 6, and then I would have to union that together with the set that includes the 0. So maybe sort of like taking a step back and thinking about this, like, you know how with like stacks and queues, our brain might look at stacks and queues and feel like we can see everything in that collection, but never forget that the actual functionality of stacks and queues, there's no way to loop over everything, right? You can't see everything. Disjoint sets is similar in that there's a lot of limitations. You can't just insert things. You can't remove things. You are only limited to the 3 functions: makeSet, which takes in a single item, findSet, and union. That's the only things you can do. Worst case, runtime, O of 1 to make a new thing. You make a new item, you throw it into the collection of sets, and you add a pointer to our dictionary of node inventory. Okay, I know these are the wrong slides now. Okay. Hang on. Hang on a second. Really quickly. Is my other version of this in here? Crap. Okay. Well, thankfully we only have 7 minutes left, so I am going to try and make it work with these things. Oh, here we go. No, we did that already. Crap. Okay. Sorry. Okay. All right. We will. Darn. Okay. Sorry, just trying to rethink how to reframe these. I will probably try and clean this up in Friday's lecture. So, okay, so that was how to make set. I'm going to spend the next 7 minutes talking about how you accomplish the union portion of things. So what we had previously, right, is we had this sort of abstract, like I drew those like little clouds and I had things sort of floating around. And I keep saying now we're moving to this idea of a tree disjoint set. So instead, where I sort of had a cloud of like maybe Joyce and Sam and Kim and Alex, things like that, now that is going to turn into a tree that's going to look like this, where what we've got here is we've got an overall root. We're going to make the overall root Joyce. And then we can see that Sam and Ken are Joyce's immediate children, and then Alex is Ken's child. Notice what's really funny and weird about these trees, that the direction of the pointers goes up instead of down. And that's because in this particular tree implementation, what we're going to do is anytime we're going to try and find set, we're going to jump into a node and then we're going to travel upwards to its overall root. And that's where we're going to find the representative. So whenever we are trying to find set, we need to have the ability to go from child up to overall root to find our representative. Also works for sets of one. Paul is his own representative. Over here, Santino's representative is Eileen. Eileen's representative is Eileen. So that's the sort of tree nature of these individual sets. Yeah, question.
Is there a reason for why like our overall root would store like a name instead of just the number?
So what's happening in this particular situation is that the names are the values we're trying to actually store. Like you could think of the names as the data in the individual vertices of the graph. The numbers are sort of standing in as like the representatives in this particular case. So the names are the important part.
Oh, so is like the overall root just like a different data structure then from the children because it contains also that like number?
So yeah, what will happen is that these nodes will have like you could have a node that has this extra field. Part of the reason I need to change these slides is because technically you don't need this. What you would do is then you would have a set node that say like each of these children, and then it would store its parent. And then the overall tree set, not the individual node object, but the tree set object, that will have a field that will store overall root, and that would point to this top node. And then that's just where you find the representative. So if you get into an individual set node and its parent pointer is null, that means you are the parent, you are the ancestor, and thus you are the representative. Okay. Again, we are going to have this separate structure to let us jump into nodes quickly. So this is a separate map. I would store it by name. The name would have a value that would point to the individual node. So for example, if I wanted to call find set of Alex, what I would do is I would jump into this dictionary down here. I would find Alex's value and I would go boop, 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 boop. There it is. I'm at the Alex node. Then I would say, okay, Alex, recurse up until we find your, top overall root. And so Alex's parent is Ken, Ken's parent is Joyce, and that's how I would eventually get to Joyce. I'm probably not going to draw out this little structure a ton from here on out, but do not forget how important this structure is. So we're not looping over all the sets to find something. We're using this map as a separate entity to store them. It's kind of like what you did in Project 3. Remember how you had to have that collection so that when you called change priority, you could go in and immediately find the thing you were looking for? Same idea. Also, part of the reason that I teach disjoint sets, because you'll find a lot of objects, a lot of data structures do employ supplemental data structures to optimize for little things like this. So a lot of times data structure implementations truly are a combination of many of the data structures and collections we've learned so far. And also, when in doubt, we just want more maps. Throw that hash table in there. We love that constant time lookup. We don't need to loop over things. We're just going to spend a little extra memory and store exactly where something is in our collection. Okay, so now we want to implement union. So if we're going to implement union, we need to take in the two things that we are going to union together. So I could try to union Ken and Santino in this way, where the first thing I'm going to do is I'm just going to find wherever Santino is. And then, you know what? I'm just going to set Ken to point to that item. Like I could just move Ken over, right? But if I did that, if this is our sort of like starting state, you can see that what I did is I took Ken off of Joyce and I just pointed him at Eileen, but that's not the functionality that I want. I didn't want to just move Ken over. I want to move everyone that is currently married to Ken or currently in a family with Ken or currently in community with Ken. All of them need to move over as well. So this is the correct way to do it, where we actually need to call find set on both of the individual items. And then we will set one of the pointers of one of those sets to point to the overall root of the other set. So originally we had Eileen, right, with, because what were we trying to do? We were trying to do Ken and Santino. So we would do find set of Ken. We'd find like Ken's and Joyce's set. We do find set of Santino. We'd find Santino as an Eileen set. And what we ended up doing is we just took Joyce and pointed her to be a child of Eileen. So I just updated one of these overall roots parents to point to the other one, which is great because both of them had originally overall root parents that were null, right? So I didn't lose anything. I just sort of tacked Joyce and her whole family onto Eileen. Now they're one big happy set and poor Paul is still kind of hanging out. Yes?
When we add, or when we create the union, do we always, or I guess, okay, I was wondering if we always maintain like the full tree, but I guess not because the order right?
Yes. And in fact, come back on Friday for me to talk in excruciating detail about how we decide who absorbs whom, and also some very tricky optimizations where we're going to continually squish the tree. Yes. Great question about invariance. So we do need to maintain this idea that we have like one overall representative for each individual set. That's a requirement. We do need to maintain the no duplicates. So anytime you call makeSet, we do need to make sure like we're not adding in a duplicate. I think those are the two key ones.